Hi, this is Mrs. LaBarbera. This is AP Physics Mechanics C, and today's topic is energy in simple harmonic motion. The objectives are: know the total mechanical energy in simple harmonic motion is conserved. Know the position where maximum and minimum potential energy or kinetic energy occurs. Understand the effect of changing the amplitude of a spring mass system, and understand the effects of friction on a spring mass system. Be able to describe kinetic energy, potential energy, and total energy as a function of position and time. Be able to sketch the graphs of kinetic energy, potential energy, and total energy versus position and versus time. Calculate mechanical energy of an oscillating system. Total mechanical energy in simple harmonic motion is conserved when friction equals to 0. The force exerted by an ideal spring is a conservative force. That's the force on the spring. And it is the net force on the spring system, so the total mechanical energy is conserved. Assume the mass of the spring itself is negligible and when there is no friction. So K at any time is 1/2 mvx squared. U at any position is 1/2 kx squared. So K plus U equals to constant. Since at A, when x equals to A or negative A, that's most positive or negative amplitude, V equals to 0. So at those points, the energy is entirely potential. So total energy is 1/2 Ka squared. Total energy is constant. So it's 1/2 mvx squared plus 1/2 kx squared equals 1/2 Ka squared. Using this equation, we can figure out Vx at any position, or we can find x with any given velocity at that position. Interpreting total energy, kinetic energy, and the potential energy bar graph in simple harmonic motion. So here is simple harmonic motion. We know at the end the total energy is potential energy. So the bar graph looks like this. Brown is total energy, so total energy equals K plus U, K equals 0 at the end. In the middle, the total energy is kinetic because there is no displacement. So the bar graph looks like this. The all energy is kinetic. There is no potential energy. How about in the middle? When x is in the middle, its potential energy is 1/2 kx squared. So this squared becomes 1/4 of A squared. So the potential energy is just 1/4 of the total energy. And the kinetic energy has to be 3/4, since these two added together equals to E. So what does graph looks like? You have more kinetic energy than potential energy. How much more? You have 3 times more kinetic energy than the potential energy at half point. How about velocity? We can find velocity if we are given x. Using this equation, we can find velocity at these 2 points, minus 1/2 A and a positive 1/2 A. Energy versus position. This is energy versus position line graph. So this green, this is kinetic energy. Kinetic energy is highest over here, and blue is the potential energy is the lowest. Ux equals 1/2 kx squared. Ux graph has to be a parabola. Ux equals 0 where x equals 0. Ux is maximum where x equals to positive or negative A. Now, since K plus U is constant, so Kx is just constant minus 1/2 kx squared. Therefore, the Kx graph is upside down parabola. Kx is maximum at x equals 0, and Kx is 0 at the end when x equals to positive or negative A. We know total E is constant because its total energy is conserved. It doesn't depend on position. What is x when K equals to U? At this point, the two graphs intersect. So this is special point when K equals to U. How do we find x? We can use conservation of energy to find x. U equals 1/2 kx squared, and E is 1/2 Ka squared. So we can find x as a function of A. X equals to positive or negative A divided by square root of 2. Next question is when K equals U, what is V in terms of maximum velocity? So again, we use conservation of energy, but at that point, the energy is totally kinetic. So 1/2 mv squared times 2 equals 1/2 mvx squared. So from here, we can solve for V equals to V max divided by square root of 2. It's positive or negative. energy versus time. Here is a position versus time graph. Since u equals 1/2 kx squared, so u is this. Take a look at this. U is always positive, never negative. U is maximum when x equals to either positive a or when x equals to negative a. U equals to 0 when x equals to 0. How about energy versus t? Since x equals to, in general, x equals a cosine omega t plus phi, so ut is just 1/2 kx squared as a function of time. How about kinetic energy? This v corresponding to this x. So when x is maximum, v equals to 0, and it's moving in the negative direction. So k equals 1/2 mv squared. As you can see, k is always positive, and k is maximum when v equals to either most negative velocity or most positive velocity. K equals 0 at the end when x equals 0, or when x equals to positive or negative a, when v equals 0 at the end. What is the function of k versus t? Since v equals dx over dt, so v equals a negative a omega sine omega t plus phi, so k is 1/2 mv squared. So this is v squared. How about total energy? Total energy is just u plus k. This is a function of u, that's orange, and blue is a function of k. The two add together is always constant. So E is constant, it does not depend on time. Take a look at this example. So in an oscillation where K equals 200 newtons per meter, M is 0.5 kilograms, and the oscillating mass is released from rest at X equals to 0.02 meter. What is the maximum and minimum velocity attained by oscillating body? Let's take a look at velocity as a function of time. From here, since the maximum value of sine omega t plus phi is 1, right? So the value of Vmax is just omega A. The maximum is positive omega A, the minimum is negative omega A. We know omega equals to K over M, square root of K over M, and A is 0.02, so we can find maximum velocity and the minimum velocity. How about maximum acceleration? Acceleration is negative omega squared times x. So maximum acceleration occurs when x equals negative a. Plug everything in, this is what you have. Continue with the same question. Now you have to determine the velocity and acceleration when the body was moved halfway to the center from its original position. So when body is halfway, x equals to 0.01. So the original position is this. When the box is moving halfway, it's moving to the left, so velocity has to be negative. How about acceleration? Acceleration is negative omega x, so acceleration has to be negative as well. To find velocity, we can use conservation of energy. Plug the position in, and that's how you find velocity. And acceleration is negative omega squared x. That's how you find acceleration. How about total energy, potential energy, kinetic energy at that position? Well, total energy is just 1/2 Ka squared. Potential energy is 1/2 Kx squared. What is x? X equals A over 2. So potential energy is 1/4 of the total energy. And the rest has to be kinetic. So kinetic has to be 0.03 joules. Okay, the effect of changing the amplitude of a spring mass system. We know that amplitude does not affect the period, because the period only depends on the spring constant and mass, right, of the spring mass system or the pendulum. But for the spring mass system, total E equals to 1/2 Ka squared. So as amplitude changes, total E changes. If A doubles, E would be quadruple. If A halves, E would become quarter. Let's take a look at this question. To double the total energy of the mass spring system oscillating in the symphomic motion, by what factor must amplitude change? So if E has to double, A squared has to double. If A squared has to double, how does that affect A? So A is proportional to square root of E. Square root of 2 is just this. So the answer has to be C. Next question, by what factor will the frequency change due to this amplitude increase? We know frequency is 1 over 2 pi k over m. This equation does not have amplitude, so frequency does not change. The answer is C. The effect of friction on the spring mass system. So let's take a look. Friction changes total mechanical energy into heat, converted into heat. As a result, the amplitude has to decrease. So let's take a look at this example. A block is set into oscillation by stretching the spring and release the block from rest at t equals to 0. The resulting graph of the velocity v versus time is shown right here. The positive direction for all quantities is to the right. So this block is released from here at when x equals to a. So it started to move in the negative direction. At this position, v equals to 0, but it started to move in the negative direction. Now, the block and the spring arrangement is now placed on a rough surface and is displayed so that the spring is compressed. Now it's going to be over here and released from rest. What does this graph looks like? So you start v is still 0 now, but v is going to start to be positive because it's going to move to the right. How about amplitude? Amplitude will decrease since neither mass nor spring constant change. So your t does not change, your period does not change. So you still have the corresponding position here. But as you move, your amplitude decreases because energy decreases due to friction. And that's it. Thanks for watching.